This is Professor Pelton. This is part 1 of Chapter 2, Section 6. So what I've stated here is all of the exponent properties that we covered in Chapter 1. And you're wondering, well, why am I giving you the properties again? What I'm trying to dictate here is um, it doesn't matter that the exponents are fractions, right? So you'll notice these are very similar problems to Chapter 1, except now we have fractional. So whether it's a fraction, decimal, or a whole number integer, doesn't matter. The properties still work. Okay, so the product property is adds. This is 5 to the 6/3, right? Because you just add the fractions, or which is 5 squared, thus 25, right? So that's the product property of exponents. So same thing here, because they need common denominators, right? So this is 2 to the 3/4, right, times 2 to the 2/4, or otherwise it's known as 2 to the 5/4, right? Okay, that'll give you a decimal because you can't do the fourth root of that, so that's fine. Okay, so power to power is multiplies. This is 4 to the 6/3, right? Or simply 4 squared, which is 16. Okay, and you're like, well, do parentheses first, do the product rule, but the problem is those are different bases. I can't combine those using the product rule of exponents because they're not the same base. But I can do the power to a power. So I get 5 to the 2/2 times 16 to the 2/4. Okay, so that's 5 to the first times 16 to the 1/2. So I can rewrite that as 5 times the square root of 16. Okay, so that gives me 5 times 4. So I get 20. Okay, because essentially 1/2 power is a square root, right? So the equivalent, I guess essentially x to the 1/2 is the same as the square root of x. It's no different, right? Okay, next problems. All right, so same thing here, parentheses first, but I can't because they're not the same base. I can't combine them. So do power to a power, which is multiply. So I get 2/2 and 2/3. So that's 6 to the 1 times, well, nothing I can do here because this is the third root of 4 to the second power. Okay, so there's nothing I can really do. So it's 6 third roots of 4. And then you can put the squared inside too if you want. It doesn't matter whether you put the squared inside or outside, really. It's really a preference as to what you want to do there. Okay, because essentially at the end of the day, what we're trying to go for is the numerator is the exponent and the denominator is the radical. Okay, all right, so we have a quotient rule, which means subtract the exponents. This is x to the 5/2 minus 1/2. So that's 8 to the 4/2. Ooh, so that's 8 to the 4/2, right? 5/2 minus 1/2. So that's really 8 squared. So I really have 64. Okay. All right. So the next one, you're like, well, it's quotient rule again, right? But I can't subtract those. The top one doesn't have an exponent. Remember, if there's no number, 1 is always the place value, right? So we really have 1 minus 1/3, which is really 3/3 minus 1/3, which is really 5 to the 2/3. Okay. All right. You can write it in the radical notation too. You can write the third root of 5, right? You can put the squared on the outside or the inside. It really doesn't matter. Either way, there's no third root of 5. That gives you a nice whole number answer. It's a decimal. Okay. So you can kind of inverse the properties too. Since I can't do the quotient rule here because 42 and 6 are different bases, I can take the 1/3 out and have 42 over 6 to the 2/3, right? So again, instead of multiplying by the 2, I just divide out the 1/3. So 42 divided by 6 is 7 to the 2/3, right? Or you can do the third root of 7 squared, and you can put the 2 on the inside or the outside. Either way is a sufficient answer, whether it's in radical form or it's in exponent form. Okay? All right, pause the video, try the student problems for yourself. Okay, so we have the product rule of exponents, which means add. So that's 3 to the 5/5, or 3 to the first, or simply just 3. Okay, same thing here. We'll need common denominators. So 7 1 to the 1/4 times 7 to the 2/4 So that's 7 to the 3/4, which is a good enough answer. You can again rewrite it as radical notation if you want, but there's not enough 7s to actually cancel it. Um, so that either way is fine. One's the exponent form, one is the radical form. All right, power to power rule is multiply. So that's 10 to the 4 halves, which is 10 squared, which is essentially 100. Okay. So again, parentheses first, but those are not the same base. You cannot do the product rule. So you do the power to power rule first. So I'm going to get 4 to the negative 1 times 3 to the negative 1, right? Because 1/5 of 5 is 1, right? So I really have 1 over 4 times 1 over 3, applying the negative exponent rule, which is really 1/12. Okay. We got a few more down here. Oh, actually, it's not quite what I want here. Move that up a little bit. There we go. That's good enough. Now we can see the problems. Okay, so same thing. Check the parentheses first. Well, those are different bases. Can't combine them. So do a power to power first, which is multiply. So I get 5 to the 3/3 times 7 to the 3/4. So I get 5 to the 1 times the 4th root of 7 to the 3rd. Again, you can put the third on the inside or the outside. Either way, there's not enough 7s to be able to come out with the 4. So 5 4th roots is 7 to the 3rd, right? That is a sufficient answer. Or you can leave it in the exponent format, either way. So that'd be what, 5 times 7 to the 3/4. So either one is a good enough answer. You can't combine them because they're not the same base. All right, these are the same base. They're both 7s. I can subtract. So that's 7 to the 2/3 minus 5/3. So that's 7 to the negative 3/3, or 7 to the negative 1, or simply 1/7 when I apply the negative exponent rule. Okay, let's see here. All right, so the next one has a missing exponent, but again, 1 is always a placeholder value, whether it's a product or an exponent. Okay, so I really have 3 to the 1 minus 1/4 with a quotient rule of exponents. So this is really 3 to the 4/4 minus 1/4, because that's what 1 is 4/4. So I have 3 to the 3/4, which is a good enough answer. You can write it in radical notation if you want, the 4th root of 3 to the 3rd, right? Either way, doesn't matter. Okay, so here, the problem is 20 and 5 are not the same base, so I cannot use the quotient rule, but I can take the half out doing the power to power rule backwards, right? So I really have 20 over 5 to the 3 halves, right? So what I really have here is 4 to the 3 halves. And if I rewrite that, that's the square root of 4, and I'll put this on the outside. So in this case, I actually can do the inside because the square root of 4 is 2. So that's 2 to the 3rd, which in this case is 8. So what I'm trying to dictate there is always check to see in radical notation if it actually can be done. Okay. All right, that is the end of part 1.